Hello everyone, I'm Rockname, a mobile application developer at SmartBank. Today, I'd like to explore how we can truly unlock the code generation in Swift. Before we dive in, to broaden our perspective, we'll first take a look at how code generation is utilized in Android development. In Android app development, we are going to look at two libraries that make extensive use of code generation. Both utilize annotation processing to generate code at compiler time. Let's start with Room, a library that provides an abstraction layer over SQLite. In Room, you can define a data access object like this. Using annotation processing, annotations such as @DAO and @query are analyzed at compile time. From these, Room generates implementations behind the scenes. I will simplify the example for clarity, but you can see how the library creates the necessary database logic for you. If you look at Swift data on Apple platforms, we see a similar pattern. Swift data uses Swift macro at model, which expands into property accessors and other boilerplate behind the scenes. Here, the accessor logic is automatically generated. In short, annotation processing and Swift macros share many similarities. Next, let's consider Dagger, a popular Android library for dependency injection. An example might look like this. By annotating your interface with @component and constructors with @inject, Dagger is able to generate the necessary container code. This is particularly powerful for managing dependencies in larger apps. Can we replicate Dagger entirely with Swift macros? The short answer is no. Swift macros only process the abstraction syntax tree around the macro's own declaration. Because of this limitation, macros cannot generate global code that spans multiple types or modules. However, this is only the case if you rely solely on Swift macros. Once we combine Swift macros with Swift package plugins and Swift syntax, we can perform code generation that affects multiple types. Let's see how that might work in practice by discussing a simplified example of generating a DI container similar to Dagger in Swift. I'll demonstrate a library I've been developing called Sword, which provides DI container functionality. I'll walk you through a simplified version of its core implementation. If you'd like to see the details, I encourage you to check it out on GitHub. First, let's outline the project structure we are aiming to support with our code generator. Here, app component is our DI container annotated with @component macro similar to Dagger. Here, and next in the data local module, we have user local data source, which is annotated with @dependency, telling us to register it into app component. Its initializer is annotated with @injected. We do the same for user remote data source, user repository, and login view model. Finally, our top-level scene root module holds the app component instance. When you build this project, we expect it to generate code that registers each dependency in an extension on app component. Now, I'd like to walk you through how we can actually implement this code generation process. We'll go through 5 steps to implement. Let's start with the first step, define macros. First, let's implement the declaration for the component macro. We define a component protocol, then declare an extension macro that ensures any class with a component attached conforms to that protocol. Next, in the implementation, we'll implement it by extending the type to conform to the component protocol. When we attach add component, it expands to conform to the component protocol. We use a similar approach for dependency macro. First, let's implement the declaration. We define it to accept a component protocol type as an argument, then declare it as a peer macro. Next, in the implementation, here we add validation logic to ensure that dependency macro can only be applied to structs, classes, or actors. If you attach a dependency to an unsupported declaration such as an enum, an error like this will be displayed. Here, since Swift macros are defined as annotations for generating global code, we don't actually generate any code in this case. For the injected macro, we follow the same approach as the dependency macro, showing an error if it's attached to anything other than an initializer. That concludes our first step, define macros. Now let's move on to the second step, configure plugin. We want to process the macros we defined as annotations on every build. To achieve this, we'll implement a build tool plugin. As a premise, we assume the plugin will be added in the top-level module. Let's take a look at build tool plugin implementation. First, let's focus on the target argument in the create build command method. This target corresponds to the target definition in the package.file. In order to generate code, we need to recursively gather information about the module to which the plugin was added, as well as any modules it depends on. So we are going to implement a method called recursive same package dependencies to handle this logic. First, we check if the target is a module containing source files by verifying whether target.source module is present. Next, we verify that the module type is not a test, executable, or macro. Then, for each dependent module, we only recurse further into modules that are defined within the same package. At this point, we've collected all the modules that the plugin's module depends on. We define the list of directories for the dependent module as our input. Next, we append a suitable file name to plugin work directory URL to determine our output path for the generated code. We pass these input and output passed as arguments to our executable target, delegating the code generation process. On the delegated command side, we use argument parser to accept the input and output arguments. This command run method is invoked every time the project builds. And that's where we implement our code generation logic. While this example focuses on Swift package-based project, you can also support Xcode projects by implementing an Xcode build tool plugin. That concludes step 2, configure plugin. Now, let's move on to the third step, parse. Using the input obtained from the plugin we set up in step 2, we'll proceed to parse the source code. First, the inputs in this command contain the directories holding source files. We use pathkit to collect the paths of all the Swift files under each directory. As a result, source file path now includes the path to every Swift file in those directories. Next, we parse each Swift file's syntax tree. By reading the source code from the file path and using Swift syntax's Swift parser to obtain the syntax tree, this is a syntax tree that looks like this. This syntax tree corresponds to app component. For example, the attributes node maps to add component. And the name node maps to the class name app component. By traversing this syntax tree, we can gather information about both components and dependencies. Then, we define a component descriptor to represent the information about each component. Next, we implement a component visitor that collects component descriptor instances. Component visitor is a class that inherits from Swift syntax's syntax visitor. This visitor traverses the syntax tree, and we can handle specific nodes by overriding the visit method. Here, we want to collect information for classes annotated with the add component macro. So we override the class decode syntax visit method. The node argument in visit contains the syntax tree information, which looks like this. First, we check whether the attribute name is component. The implementation looks like this. We cast each attribute to the expected types, and then extract the attribute whose name is component. Because we need to handle arbitrary macro names for both component and dependency, we put this logic into a separate helper method. Next, we verify that the component attribute we found is not nil. Finally, to retrieve the class name annotated with add component, we access node.name.text, initialize a component descriptor, and store it as a result. Returning to the command's implementation, we walk each Swift file's syntax tree with a component visitor. This collects all the classes annotated with add component. Similarly, we create a dependency visitor for the add dependency macro. Oops, sorry. That concludes step 3, parse. Next, let's move on to the fourth step, validate. Here, we apply validation to the component descriptor and dependency descriptor objects we gathered in step 3. For example, if a type annotated with @dependency does not have an initializer annotated with @injected, we want to show an error message like this. To display an error, we need to write to standard output in the following format: which file, which line, which column, and whether it is an error or warning, so it can present the appropriate message. To specify where the message should appear, we need to know the source code location of the error. To handle this, we add a source location property to the descriptor. Source location is a structure provided by Swift syntax that carries file and line and column information. Then, in our visitor, we store a source location converter and use it to extract a source location from the relevant code, or relevant node. And back in the command, we write logic that validates the descriptor and transforms it into the normalized model. If we find that the required @injected initializer is missing, we emit an error accordingly. We perform similar checks for component descriptor as well. That concludes the fourth step, validate. Finally, let's move on to the fifth step, generate code. We'll generate code using the information we extracted in the previous steps. Ultimately, we want to produce something like this. If we try to build the code as plain strings, however, it becomes difficult to manage readability. String-based generation requires a lot of manual handling for line breaks and indentation, which hurts maintainability. By contrast, if we use Swift syntax builder, we can rely on result builder syntax to create a more intuitive, readable, and extensible code generation process. The generated code forms a syntax tree that looks roughly like this. First, we set up the outermost node with calling code block item list syntax. Next, we create an extension degree syntax node as a child by passing extension degree syntax to the items builder parameter of code block item list syntax. Then, we define variable degree syntax nodes as children of extension degree syntax by passing them to the member block builder parameter of the extension degree syntax. We place all these node constructions into a render method in our command, and then convert the resulting syntax tree to a string. When we call the formatted method on render result, it helps align white space and line breaks according to the standard formatting rules. Finally, we write the resulting string to the file path we obtained as output. That's the fifth step, generate code. Now, if we build our sample project and the build succeeds, we finally generate the DA container code. That's it. To recap our journey, we define our Swift macros as annotations so the compiler knows where to expand logic. We set up a build tool plugin ensuring our code generation runs automatically at every build. We parse the .swift files with Swift parser, then walk the syntax tree using syntax visitor to find annotations. We validate each macro usage and, if needed, report errors or warnings with source location information. Lastly, we create the new source files using Swift syntax builder for clean, structured output. I hope this sheds light on how to unlock even more possibilities with Swift code generation. Thank you so much.